That's one big crystal, basically. So now what he's going to do is he's going to pour the solution on top of this. I think it's on top of this. And what happens is it almost looks like he's pouring a solid. This is what happens when it's so super saturated, it starts to crystallize instantly. So he makes like this tower. It's pretty cool. Sodium acetate can do this very well. So again, it looks like he's pouring a solid, which is just weird to say. So it's pretty cool. I can't do this demo. It's just too finicky. It's too fragile of a situation. You need a very clean flask. You need brand new chemical. It's very hard to do. And it's just more of that, so I'm going to stop it. But you see, here's another super saturated solution. If that was sitting on this table and I kind of jumped up and down, or I shook it and it kind of got some ripples going, it might force it to crystallize, just the movement. So it's very hard to kind of do this in real life. I think it's very hard, but this person is good at it, so I show the video. So that's a good example. Same principle as rock candy, except a little different. We're not going to be pouring it like that. But that's precipitation from supersaturated. So that's it. I just wanted to finish that because we got chopped off yesterday. Before we take notes, go to that nuclear chemistry quiz. Go to number 10. Emily, can you hit the lights, please? Thanks. Number 10 and number 7. Both are asking the exact same question. I wanted to make this clear because I don't think I was clear when we were doing notes on this stuff back when we were doing this. Natural transmutation, if you look at number 7, it says which reaction is natural transmutation? The answer is number 1, because one element decays into two other, it gives off radiation, that's alpha, and it turns into uranium. So natural means it does it on its own. 2, 3, and 4, number 7, are all artificial. Well, if you look at number 10, it doesn't say natural decay, it says spontaneous nuclear decay. What does that mean? Spontaneous means it kind of just happens on its own. So that's kind of the same thing as natural. So 7 and 10 are basically the exact same question. I wanted to just make that clear. So 10 is the same thing as natural. The regents could ask you, unfortunately, 3 different ways. It could say natural transmutation, natural decay, spontaneous decay. I guess those are the 3 common ways that they will ask. It all means the same thing. All right, so there, number 10, the answer is 4. It's the same explanation as number 7. I just wanted to explain that because it probably wasn't clear. All right, so that's that. You can put that away. Go to your notes. Now, what we're going to learn is, you already know some of this, factors that affect solubility. So keep table G out. We'll talk about table G a little bit more. Talked about that. We talked about that. Talked about that. Oh, real quick review. What's an electrolyte? Hannah, what's an electrolyte? Good. Why is it called an electrolyte? You can look it up. What do electrolytes do? They conduct electricity in solution. So they produce ions. Those ions are moving around. That's what allows electricity to pass through it. Good. All right. Get rid of this here. That's fun in lab. We don't have lab today, right? Period 5 people? Right, we had it yesterday, so tomorrow. Right. Okay, here we go. Factors that affect solubility. All right. Factors that affect solubility. All right. What do you guys know already? Actually, it's probably E factor, right? Isn't affect like how you feel about things? Anyways, what do you guys know already? How do you change the solubility? Heat. So temperature is one factor. Very good. And let's talk about that. Most solutes. So go to table G. Most of those solubilities. What happens to the solubility? So look at the y-axis as temperature goes up. What happens to most of them? Does the solubility go up or down? It goes up. So for solid solutes, as temperature increases, that equals solubility increase as well. What does solubility mean? It means you can dissolve more in the same amount of water. Okay, look at KNO3 for example. That one is ridiculous. What does that mean, ridiculous? At 20 degrees, room temperature, pretty close, you can only dissolve about 35 grams. If you heat that water just 50 degrees, I mean 50 is a lot, but if you heat it to 70, you can dissolve 133 grams. So the increase in temp really increases that solubility. That's for solids. Liquids and gases. Now, I'm going to put liquids in parentheses because it's not always true, but for gases this is true. So really we're just focused on gases, but sometimes liquids too. Bless you. As temperature increases, solubility decreases. So those examples on table G are HCl, I think it's SO2, yeah, SO2 and NH3. So those three on table G, those curves go down. So the solubility on table G, so if you can look at table G after you get done writing that, if you go to table G and you look at NH3, someone tell me, what is NH3's solubility at 0 degrees Celsius? How about Pat? NH3 at 0 degrees. What's the solubility? 90 grams. You can dissolve 90 grams of it at 0 degrees. Michaela, what is the solubility of NH3 at 100 degrees? NH3 at 100 degrees. What's the solubility at? About. So go to 100 degrees on the x-axis, all the way bottom right, and then just go straight up until you hit the NH3 line. 7, 6, 7, 8, yeah, around there. 7, we'll say 7. So at 0 degrees, you can dissolve 90 grams. At 100 degrees, you can only dissolve 7 or 8. So that's what I mean. The solubility goes down when we increase the temperature on gases. We're not going to really talk about liquids. These three are gases on table G. So ammonia, NH3, you would go buy ammonia in the store, it's the liquid, right? That's because it's really ammonium hydroxide, NH4OH. I talked about that in lab, that when this is in water, it changes. Pure ammonia is a gas. So these three gases don't dissolve well the hotter it gets. Let's talk about why. There's a lot of chemistry explanation there. And we'll talk about soda. Who's it going to be? Dylan, you like soda? Sometimes. All right, what kind?
Root beer.
Root beer. All right. What brand? Or it doesn't matter. Whatever. Generic root beer. Okay. Anyone else a root beer fan? Okay. Shane, emphatic. All right. Anyone? Dr. Pepper? I mean, I don't drink soda anymore, but when I used to drink a long time ago, I had Dr. Pepper. It's got that little kick to it. It's nice. Anyways. So, where do we keep soda? In the fridge, or when I lived, well, my dad's, so my parents were divorced since I was little, but so my dad's, we had soda, but we didn't keep it in the fridge. Where else could we keep it?
Basement.
Basement? Where else? That's not where we kept it, but close. Closer. Well, sort of.
Garage.
Yeah, garage. We kept it in the garage. So what's the theme here? Fridge, basement, garage. Cold. Why do we want to keep it cold? Don't just tell me it tastes better. There's chemistry behind that. Especially if you open it. So I'm not talking about a can, because cans you can't really reseal. I know they make those things you can put on there. Forget that. Let's talk about a 2-liter bottle of Dylan's root beer. Okay? So, you should make root beer. Dylan's root beer has a nice ring to it. So, we have 2 liter of Dylan's root beer, and we drink a glass, and we put the top back on. We put it back in the fridge, or probably in the fridge, but I suppose you could put it back in the basement or in the garage. You're not going to leave it out on the counter at room temperature, or if it's the summer, definitely not. Why? Why do we keep it cold? It gets flat faster if it gets warm. Why? I just taught you that. Table G shows you that. If you increase the temperature on gases, they don't stay dissolved. So, let's draw a picture. draw, well, if you want, you could draw, you know what? We could draw a 2 liter. I'm just going to draw something that looks, I don't know, something like a 2 liter. You guys can do what you do. I don't know even know how I'm going to do this. We're just going to do that. That's what I'm doing. Okay. So there's our 2 liter. Okay. And then we're going to have another one next to it. You guys can probably do a better job than me. Oh boy, that's just terrible. Hold on. I can do a little better. Maybe not. Okay. Okay, so here's our soda. Okay. All right. So draw a little bit of space up there because you drank some of it. All right. Don't spend 5 minutes drawing your bottle. So here we're gonna say, here's our root beer. Dylan's root beer. Dylan's root beer. And we're gonna say in here at this, the temperature here. Let's say we leave it on the counter. So let's say in here we're at 25 degrees Celsius. Here, same scenario, but we're at 0 degrees Celsius. So same thing. So 25 degrees and 0 degrees. Tops on both of them. Okay. I'm gonna draw some things. You draw exactly what I draw. Make sure I don't screw this up here. Okay. If you are picking up what I'm putting down here, that's good. If not, I'll explain. So this little picture explains why we keep soda cold, especially if we opened it already. What are the little circles I'm drawing? They're supposed to be like little bubbles. What are that supposed to be? So these little thing is CO2, gas. I could actually draw something that looks like this. Here's a C, here's the CO2, but that would get kind of tedious. I don't have time for that. So let's say that one little thing here represents CO2. So label that so you know what you're looking at. So what am I trying to show you? What's the heat doing to the CO2 that's not doing here? And be careful on how you word this. If you say the wrong word, throw a marker at you. Just kidding. I'll tell you what you're not supposed to. Don't say it's evaporating. That doesn't make any sense. It's already a gas. So what is it doing here? What's the CO2 doing here that's not doing here?
Rising.
Rising, good. That's a good word. You don't get hit with a marker. What else? What's this called, this part of the picture here? What's that called? That's the soda. Okay, now in chemistry, what do we call that? A solvent would be just water. There's more than just water there. Solution. So here's your solution. Up here is not the solution. So what's the CO2 doing here that it's not doing here? Escaping or leaving the solution. That's the right thing. Good. No markers for you. So here's what I want you to do. I want you to draw a couple arrows going up. Here we're not even going to draw any arrows. The hotter or warmer the soda gets, the more CO2 leaves the solution. So we're going to write that. As temperature increases, more CO2 leaves the soda. How do you combat against the CO2 leaving the solution, leaving the soda? You keep it cold. That's why we keep it cold. A lot of people will say, well, it just tastes better. Yeah, maybe it does, but maybe we're just conditioned to that. It probably tastes exactly the same, warm and cold, but I don't know. Don't drink it anymore. But we don't want the CO2 to leave the solution. This will get flat. It'll taste blah, whatever. You want the carbonation. You want the CO2, so you keep it cold. It doesn't leave the solution. Penguins, goats, sheep, they all act like CO2 molecules. I've used this analogy before. Penguins in Antarctica, especially after they give birth, I think the guys, right, the males sit on, well, they look like they sit on them. They're not sitting on them, but they're all huddled together. And protect the egg, and females go hunt. Right? We've talked about this. Okay, it gets like negative 55. Literally, that's the temperature, not like wind chill. So what do all the penguins do? Huddle together. Why? Preserve heat. They're cold. They huddle together. Look up here. The colder CO2 huddle together, and the penguin analogy breaks down here. When gases huddle together, do they become more dense or less dense? What's density? It's how closely packed particles are. So if particles are really close together, they become more dense. So if gases become more dense, they become, I hate saying this, but I'm going to tell you because it just makes sense, heavier. They're not heavier, but they sink. So the gases are more dense, they are less likely to leave or escape the solution. Here, if you keep jacking up the temperature, if you were to boil soda, it would go flat almost instantly because the gas spreads out, leaves the solution because it's less dense. So just simply drinking soda, putting the top on it, and putting it in the fridge, there's lots of science and chemistry behind why you're doing that. People aren't thinking about that when they put it in the fridge. But that's all of the things we just talked about is why we put it in the fridge. And that's why the CO2 stays in solution, and it doesn't if you heat it up or if you let it sit on the table. Or if you put it in a glass and just let the glass sit there. Okay, you need the top too, and we're going to talk about that next. So as temperature increases, more CO2 leaves the soda, and the reason for this, it becomes less dense. It becomes less dense. Therefore, it will leave the solution. Like helium balloons will float. They go up to the atmosphere. They'll just keep going up, up, and up, and up until it pops or until it essentially explodes. Same concept. Things that are less dense in the soda, CO2, will leave the soda. So the whole penguin analogy is to help you understand they huddle together. The colder they are, they huddle together, they stay dense, they stay down, they don't leave the solution. Hopefully it makes some sense. So I don't think it's a great idea for you to drink soda, but once in a while is okay, I guess. So next time you drink soda, think of the chemistry. You get a little chuckle. Or think of don't. Either one. Questions? Okay, so that's temperature affecting solubility. I didn't go on and on and on explaining why solids, so if you look at table G, why most of these are going up. The reason for that, I don't need to write it, is you're giving the water more energy. So the water has more energy to rip apart, like on that worksheet we had the other day. If I can find it quick. This one here. So the water comes in and rips apart the salt crystal. The more energy you give the water, so you heat it up, the faster and better it can do that. It's just more efficient at breaking down solids. I'm not going to really give you notes on that. All you need to know is, can you explain this? Can you explain, as temperature goes up, the solubility of solids go up, meaning you can dissolve more. And then this is the explanation as to why those three gases decrease in solubility. It's because of density, essentially. Okay? You're making the gas less dense the warmer it is. All right? So those are the two dynamics you need to know. Increased temp, solids you can dissolve more, gases you can dissolve less. So you want it to be cold to dissolve gases. That's the key here. Okay. All right, so that's that. The next factor that affects solubility, and we'll be drawing some more pictures. What do you guys think? There's really three. There's temperature. Concentration is one. We'll talk about that later. Let's not talk about that right now. And then this factor really only affects gases. What have we learned in here that only affects gases? I'm doing it right now. Just chilling out. No, I'm not doing it. My feet are doing it. What? Pressure. Pressure only affects gases. How come it doesn't affect solids and liquids? Max, how come pressure only affects gases, not solids and liquids? Gases are moving because they have, say it. You were just about to say it. Space. So gas particles have space to be moved. Solids and liquids are this close together. If you put pressure on it, okay, move a little bit, big deal. Okay? So pressure doesn't really affect solids and liquids. Pressure affects gases dramatically. So pressure is the other factor. Now, here's where it gets a little confusing. Write it down, then I'll explain it. If the pressure above the solution is increased, if the pressure above the solution is increased, the solubility of a dissolved gas will increase. It's called Henry's law. Solubility of a gas in a liquid is directly proportional to the pressure of the gas above the liquid. I don't need to tell you it's Henry's law. I don't need to give you the fancy definition. That's what it means. If you increase the pressure above the solution, you increase the solubility of the gas in the solution. If you decrease the pressure, then you decrease the solubility. It's a direct relationship. Right? So let's draw a graph. So if this is the pressure above the solution, and this is the solubility of the gas, here's your solubility, here's the pressure above the solution. What does the graph look like? Marcy? Very good. Direct relationship. That's what I'm trying to get you to understand. This also applies to Dylan's root beer. How? We just talked about keeping it in the fridge or the basement or the garage. We explained why we do that. We didn't explain why we put the top back on. If you don't put the top back on the 2-liter, what happens to all the CO2? It escapes into the environment. So we put the top on. Next time you open it up, what's that noise you hear? What's that being released? Don't say pressure. You are releasing pressure, but it's CO2. Yes? That's what you're going to say. Okay. So let's draw some pictures. We'll draw a couple. We'll make it easy. I'm not drawing soda bottles here. Just draw a couple beakers or containers with some sort of lid on top. Watch glass, I don't know. Some sort of lid. Okay, it has to be a sealed container. Otherwise, air pressure is affecting this here. So draw some liquid halfway. Let's say the air pressure here, or the pressure inside this container here is 1 atm. Let's say this is, I don't know, 5 atm. Again, we're going to draw little circles for gas. So 1 atm, okay, 1 atm, we're going to have less particles dissolved than we have for the 5. So we're going to draw maybe 1, 2, 3, 4, 5, and then we'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Over here, we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then we'll only draw about 3 up here. So what I'm trying to show you here is that, and I'm going to draw an arrow, a couple arrows going down, is that if you increase the air pressure above the solution, it literally is forcing gas back into the solution. Why? If you put enough pressure on gas particles, what do? They move closer together, they become more dense, so they stay dissolved. It's the same explanation as the temperature. So who remembers the 2 conditions for an ideal gas? If you want a real gas to behave like an ideal gas, it's temperature and pressure. What are the 2 scenarios? Ideal, remember, is when the gas expands till it doesn't exist. So what 2 conditions? Temperature and pressure. High temperature, so it can move around and get away, and low pressure, so you can release the pressure, it will expand. What we're talking about is the exact opposite. If you have a can of soda, a bottle of soda, whatever, and you want it to stay fresh, you want to keep the top on, that builds the pressure. You want to put it in the fridge, that keeps it cold. Both are working in opposite of ideal. You don't want an ideal, you want the opposite. You want them close together, you want them forced in the solution. So, over here, what we're going to say is an increase in pressure increases the density of the gas. of the gas, sorry. Therefore, it stays in solution. Increase in pressure, increase the density of gas. It stays in solution. Okay, over here, if we decrease the pressure, that decreases the density, so the gas leaves the solution. So what I'm trying to get you to understand, and not memorize, because that doesn't help you learn much, understand why we keep soda in the fridge, why we keep the top on it. Here's the chemistry behind it. This is called Henry's Law. You don't need to know that. But if you increase the pressure pushing down, then it stays in solution. If you take the top right off, then of course it's going to leave because you're letting it leave. You're not keeping that gas together. You're letting it expand. Last thing with this. Can I erase this? Unfortunately, I don't think you're going to have homework. However, you do have homework. Chapter 1, due tomorrow. All right. Okay. Last thing. All right. Draw a couple soda bottles again here. Or you can just pay attention here. So there's. Yeah, that's better, right? Sort of. I can't draw the next one, but I'll try. Okay. Stay with me. Let's say you drink some of the soda, put the top back on, just put the bottle back in the fridge. This time you drink some, you squeeze it so the level of the soda rises to the top. You squeeze it, then you put the top on so it stays squished. That's the one on the right. Which one's going to stay fresher longer? I actually had a student literally do this. He did science. He bought 2 identical 2-liter bottles. He drank both the same amount every day, and one he kept squeezing the best he could, and the other one he didn't. So he proved it. He did science at home. Which one stays fresher longer? You just learned how pressure affects solubility of gases. Which one do you think stays fresher longer? Food for thought. We'll talk about it tomorrow. Bell's gonna ring. So think about which one stays. It's not really like homework, but just think about it. Which one stays fresher longer?
They're all the same. I think whoever has the most G Jordans.